Good day, sir. Good day, everyone. I am Deck Cadet Caparal, and we are the Group 2, and this is our Prelim Assignment Week 3. The learning objectives. At the end of the lesson, the students will be able to describe the importance of ship's turning circle in ship handling. Second, compare the turning circle in ballasted condition to the turning circle in loaded condition. So, ship's turning circle. A ship's maneuvering characteristics define its ability of turning, yaw checking, course keeping, and stopping distance. When a vessel fitted with a fixed right-hand propeller, she would benefit from the transverse thrust effect, and her turning circle, in general, will be quicker and tighter when turning port than to starboard.
Good day, sir. I'm Gadikalo, and I'm here to present the fifth slide for our report. Ship turning circle. Ship turning circle. The longer the ship generally, the greater the turning circle. The type of rudder and the resulting steering effect will decide the final diameter, with a clearance between rudder and hull having a major influence. The smaller the clearance between the rudder and hull, the more effective the turning action. The following factors will affect the rate of turn and the size of turning circle. Number 1. Structural design and length of the ship. Number 2. Draught and the trim of the vessel. Number 3. Size and motive power of main machinery. Number 4. Distribution and stowage of cargo. Number 5. Even keel or carrying a list. Number 6 is the position of turning in relation to the available depth of water. And the last is number 7, the amount of rudder angle required to complete the turn.
Good day everyone, I am Cadet Korea. So I'm going to discuss these external forces affecting the drift angle. So we have here the draught and trim. So the deeper a vessel lies on the water, the more sluggish will be here response to the helm. On the other hand, the superstructure of a vessel in the light condition and the shallow in a draught is considerably influenced by the wind. So the trim of a wind vessel will influence the size of the turning circle in such way that it will decrease in the ship is trimmed by the head. So next slide is we have here the TCD maneuvers. The ship ran at full speed with rudder helm 35 degrees P or S throughout this trial. So as we can see in this slide or picture, we can see the TCD or the tactical diameter. So we can see here the drift angle of the ship, the path of ship's center of gravity, and so on and so forth. So that's all.
So good everyone, my name is Nelson Danaco, and the external forces affecting the drift angle. So motive power. The relation between power and direct displacement will affect any vessel's turning circle performance in the same way that a light speedboat has greater acceleration than a heavily laden or carrier. It should be remembered that the rudder is only effective when there is a flow and water past it.
So good day, I am Cadet Ebuesa. So external forces affecting the drift angle, distribution and stowage of cargo. Generally, this will not affect the turning circle in any way, but the vessel will respond more readily if loads are stowed amidship instead of at the extremities. Merchant ship design tends to distribute weight throughout the vessel length. The reader may be able to imagine a vessel loaded heavily fore and aft responding slowly and slugishly to the helm. So, stowage should aim at distributing the cargo for any particular load or discharge port equally in every hold, such that all the cargo handling equipment is employed to full capacity throughout loading and discharging operation.
Good day everyone, I am Deck Cadet Zaran Sarkasa and I am here for the Group 2 and we're going to talk about the external forces affecting the drift angle. So, even keel or listed over, when engaged in trials, a new vessel will be on an even keel when carrying out turning circles for recording the ship's data. So, in this condition of even keel cannot, however, always be guaranteed once the vessel is commissioned and loaded. So if a vessel is carrying a list, it can be expected to make a larger turning circle when turning towards the list, and vice versa.
Good day everyone, my name is Cadet Istaka and I'll be talking about the external forces affecting the drift angle. Available depth of water, the majority of vessels, depending on the hull form, will experience a greater resistance when navigating in shallow waters. A form of interaction occurs between the hull and the seabed, which may result in the vessel yawing and becoming difficult to steer. She may take longer to respond to the helm movement, probably increasing the advance of the turning circle and increasing over the transfer. Rudder angle. Probably the most significant factor affecting the turning circle is the rudder angle. The optimum is one that will cause the maximum turning effect without causing excessive drag. If a small rudder angle is employed, a large turning circle will result with little loss of speed.
Good day, sir. I'm Cadet Estrada. Now, explain to you the external force of affecting the drift angle. So, drift angle and the influencing force. When a vessel responds to helm movement, it is normal for the stern of the vessel that is presupposing the motion. So although the below movement is the desired vessel, resultant motion is one of grappling in the sideways direction at the angle of the drift.
So, good day everyone, my name is Cadet Kenti Gamali and my topic is all about compare the turning circle in a ballast condition to turning circle in loaded condition. So, meaning, a turning circle is a turning ability to fully loaded condition is much larger than that in a ballast condition in some cases, or a turning circle rather in a trim by stern condition has larger even keel condition. So furthermore, the sea trial test for new ship is mostly executed in a ballast condition.
Good day everyone, I'm Cadet Hamisula Og Zulkent. So, turning circle, normal full loaded condition with maximum rudder angle. So, the full sea speed is 104 RPM. So, the starting knots of this ship is, for the port side is 25.52 knots and the other side, which is the starboard, is 25.52 knots. So, they have the same knots, but if the turning circle will start, so the port side knots will 16.9, 11.5 knots onto 9.7 knots. And on the other side is, if the turning circle will start, so the knots of her ship will be 17.0 knots to 12.2 knots and 11.34 knots. Also on the other slide is normal ballast condition with maximum rudder angle, fall ahead RPM. So as you can see on the in the slide, they have the difference knots and nautical miles, because this is the normal ballast condition with maximum rudder angle, fall ahead RPM, and this one is normal full loaded condition with maximum rudder angle.